All right, we're going to talk about everyone's favorite SN2 mechanism today, as well as thinking about elimination mechanisms, a lot of acidity and basicity today. So here's our learning objectives. We're going to learn about ethers as well as the sulfur version of ethers, which are called sulfides or thioethers, and how to make some of those. So, we've started getting into this a little bit already. So let's dive right in and talk about some ethers. All right, so this is learning objective 17C. We're already in chapter 17. And this is going to involve a mechanism that you already know, though, but it is a 4P. So it's the 4 Ps of formation. This is pretty specific that these are unsymmetrical ethers. All right, so not symmetric ethers, those are a little easier to make. So these are unsymmetrical ethers, and these are going to be made from alkoxides and primary alkyl halides. And if you're following along in the book, this is chapter 17.6. So our sulfide stuff actually was started in chapter 16, but we decided to move it here. So you're going to see some chapter 16 shout outs in this lecture. All right, so let's start to think about this. We need an unsymmetrical ether, and our learning objective says that we're going to start from an alkoxide. So an alkoxide is the suffix IED, means that we have a negatively charged compounds, right? This is an alkoxide, right? It came from an alcohol, so negatively charged is what that means. So of course we need to have our counterion. Counterion doesn't really matter. I'm just going to use sodium in this case. A lot of bases that you would deprotonate with this have a sodium counterion, but you could have potassium or something like that if you wanted. All right, so this is going to be our nucleophile in the reaction. We see that's a good candidate for nucleophile. It's negatively charged. And then we're going to have a primary alkyl halide. In this case, I'm going to use methyl. So X here equals chloride, bromide, iodide. Is a primary alkyl halide. This is going to be our electrophile. We're going to talk about the reason why that primary alkyl halide is so important. So we'll just use methyl as an example, though. Okay, so what we have in this reaction is an unsymmetrical ether as our product. So we have RO that is now bound, in this case, to our methyl group. Our byproducts of the reaction are, of course, our sodium plus, and then our X minus from our halide. We see that this is an unsymmetrical ether. Right, and so sometimes for unsymmetrical ethers, we call this the Williamson ether synthesis. All right. So our alkoxide is a very strong nucleophile. So let's think about that R of our alkoxide. This R can equal a lot of different things. So it can be branched alkyl groups. It could be aryl groups. Be a lot of different things. This is the less important component to really be specific about. All right, we can have something, as we're going to see in this mechanism, we can have something that is going to be, for example, a tertiary alkoxide and have a very tert-butyl group on there, for example. All right, so why doesn't this matter? This doesn't really matter as much for the identity because we have our nucleophile that's starting from that lone pair of electrons that's going to attack our methyl group. And then we have X as our leaving group. Right, so the mechanism, it's just an SN2 mechanism. That's why oftentimes we think about SN2 mechanisms. We don't care as much about the nucleophile, but we do care a lot about the identity of the electrophile in the SN2 mechanisms. So let's talk about that next. All right, so our alkyl halide. We said that this needs to be primary. So this is, for example, methyl or ethyl. All right, so when we're thinking about an SN2 mechanism, we need to start to think about why this would be that we can only have these primary alkyl halides. Right, the reason is we're going to compete with E2 elimination mechanisms. All right, so if we had, for example, our alkoxide here, that's very strong base and nucleophile. If it's a strong base and a strong nucleophile, it can sort of do the thing that it's going to behave as a base instead of a nucleophile. So, for example, if we had a secondary alkyl halide, because this is more hindered, and the SN2 reaction is going to be harder, we would get an E2 elimination mechanism instead. So instead of the alkoxide adding into the, to have our leaving group, like our bromide leave, instead it would just deprotonate, and then we would go ahead and get an elimination reaction. So this is a 2301 sort of review here, because the SN2 mechanism is slow. And that's because we have a secondary alkyl halide. So at the end of the day, our products would be our ethanol, or sorry, not ethanol, just our alcohol. And then we would just have cyclopentene. Our byproducts of this reaction, we would still have our bromide around and our sodium as well. Right, so we cannot use anything other than a primary alkyl halide. All right. So let's review how we make this strong electrophile or nucleophile, this alkoxide. This is just some acid-base chemistry. All right, we would just take an alcohol. And we would take a good base, something, for example, like sodium hydride. Learned a lot about hydride reagents acting as reductants. Well, hydride reagents can also act as good bases as well. So what we would see in this reaction is our hydride deprotonating that OH bond, returning those electrons to the oxygen after breaking that OH bond. And we would get out at the end our alkoxide that's negatively charged with our sodium counterion. And then the byproduct of this reaction would simply be H2. So one of the H's coming from our hydride, and one of these H's coming from our alcohol. All right, and then we could go ahead and use this alkoxide. So let's see, once we form that, let's see this entire sequence that we could have. So say, for example, we had phenol. Right, we said the identity of this compound doesn't matter as much. And we would take something, a base like sodium hydride. Other strong bases work as well. And we would go ahead and we would deprotonate. We would form our alkoxide. And that could then start to engage in our SN2 reaction. And let's choose an electrophile. How about ethyl iodide? Have our electrons do that SN2 reaction. Our electrons from alkoxide come in, attack the carbon-iodine bond, have iodine leave. Then our product would be our desired ether. And our byproduct we carry through is our sodium, as well as our iodine. Right, so that would be the whole sequence. So if you're given an alkoxide, you don't need to worry about making the anionic compound from that. You would just go forward with the second half. But if you're given an alcohol and you need to deprotonate it. So sodium hydride is a very strong base, right? Because alcohols are challenging to deprotonate. Sometimes in halides, you might see sodium metal doing this as well. So that would be through a different mechanism than the traditional deprotonation. All right, so we have a lot of SN2 chemistry today, all right? And a lot of acid-base chemistry, so less complicated mechanisms than what you are typically seeing in this class. So it's a nice little break from some new mechanisms. All right, so this we can think about for thiols, which are the sulfur version of alcohol. When we take a look at, periodic table is not down. When we take a look at our periodic table, we see that oxygen and sulfur, element 8 and 16 are in the same row, so they're going to behave similarly, but they do have some different properties, all right? So that's our next learning objective, is dealing with thiols. So learning objective 17D is going to be a 4P reaction. These are some SN2 mechanisms as well. So the 4P is for the formation of thiols. So I'll put in parentheses sulfur anil-based alcohols. That's a new functional group for you. And these are going to be from alkyl halides by nucleophilic substitution. As I said before, we have some shout outs actually back to chapter 16. So this is 16.12. Question. Oh, thank you. Question. That is just an error. This should be a negative charge. Thanks for catching that. So we have the lone pair of electrons on hydrogen. So that should be negatively charged. Yeah, thanks for catching that. All right. So we're going to make a thiol. All right. So this is what our learning objective is going to focus on. So what we're going to use in this case is our nucleophile is going to be the potassium salt of SH. All right, so the analog in alcohol chemistry or oxygen-based chemistry, this is like potassium hydroxide. You can use sodium hydroxide, doesn't really matter. This is our nucleophile. And then we're going to have an alkyl halide. Now notice I didn't have anything about any problems with things that are not secondary or tertiary. So X here can be chloride, bromide, iodide. This is a bit more forgiving of a reaction. So our electrophile. And then our product is going to be our thiol. All right, so we're going to have our R from our alkyl halide. It is now bound to SH. Right, and this is basically an alcohol, but a sulfur version. All right, so we call this thiol. We can just keep track of everything. We can say K plus, X minus is our byproducts. All right, so that's how you make a thiol. All right. So as you can imagine, this looks pretty primed for an SN2 mechanism. So for an SN2 mechanism, we think about our electron density on our sulfur with that negative charge. We think of our alkyl halide with that really nice leaving group that is our X. We would go ahead and we would take electrons from the sulfur and that negative charge. We would attack our R group and we would have our X group leave. Right, so pretty easy. So we're going to make thioethers. We just learned how to make ethers. So we're going to make thioethers. So as you can imagine with thioethers, we probably want to start with a thiolate, just like up here, we wanted to start with an alkoxide. So we want to start with something that's negatively charged. So for this thiol, we can, of course, just use a base. And in this case, we'll use sodium hydroxide. All right, you don't need sodium hydride because of the SH acidity. All right, these are much easier to deprotonate. You don't need that super strong sodium hydride base. Would it work? Absolutely. But you can use something that's a little bit more conventional. And if we did this, we would get our R S minus with our sodium counterion. And the byproduct of this reaction that would be pretty easy to get rid of is going to be H2O. We call this a thiolate. So just like an alkoxide, the IDE means it's deprotonated. The ate suffix ATE also means that as well. Right, I'll give you all a second to catch up with writing. All right, so now this learning objective is going to look very, very similar to the one that was 2 before. It's the formation of thioethers. All right, so this is learning objective 17E, and this is another 4P, and we're going to see our SN2 mechanisms again. So the 4 P's of formation of thioethers. So the sulfur version of an ether from alkyl thiolates and primary or secondary alkyl halides. Now we've jumped back to chapter 17. So that's the reason I moved the learning objective previously into this chapter, because they're pretty well connected. Right, so this is going to look a lot like the Williamson ether synthesis, where we took an alkoxide and an alkyl halide, except we have our thiolate here, and I'll note the one difference. All right, so we have our sulfur compound that's negatively charged, our thiolate. That's going to be our nucleophile in this reaction, right? We see a lot of electron density around sulfur. We're going to have our alkyl halide. So R prime can be equal primary or secondary in this case. Our X is going to equal chloride, bromide, iodide, sort of the classics that are good leading groups. And this will be our electrophile. Here's to start to be able to see some of the patterns that are going to happen. So we can kind of predict based on an analogy to our ether synthesis what we're going to get out of this. And what we're going to get out is this nice unsymmetrical ether compound. And we call this either, unfortunately, there's 2 names for this. We call this a thioether. I like that name better because it's analogous to our ether, but you will also hear these called sulfides. And sulfides are used a lot more in biological terms. Sulfide bridges and things like that are quite important in biological systems. So it's just creeped into the organic chemistry literature as well, because a lot of biochemistry and chemical biology has to do with organic chemistry. Let's balance everything out. We have our sodium plus and our X minus. All right. So let's do a practice problem. Let's see what this would look like with some actual substituents. All right, so let's say we have methyl sulfide. All right, and let's actually use, just so we can see, a secondary bromide. Now, we could not have used this before with alcohols, but we see that we can do an SN2 reaction, have our electron density start from our a lone pair on the negatively charged sulfur. We're going to attack our bromide and have it leave. All right, we have our methyl sulfide, and we have our next substituent, which is that cyclohexyl group. Byproducts being sodium plus, Br minus. All right, so why can we do this? I wish I could tell you all the rules are same for oxygen and sulfur, but that's not the real world. We have to go with what's true rather than what's convenient. And so in this case, we see that it works with a secondary. So why is this? This is because our thiolates are great nucleophiles and they're less basic than alkoxides. So they're not as good of a base. So that deprotonation of that CH bond for the elimination, we could have done this, but we don't deprotonate that because this is not as good of a base, but it is a better nucleophile. And the reason why it's a better nucleophile, sulfur is larger, it's more polarizable, it's more willing to give up electrons, it's not as electronegative. And so for that reason, we can get around the problem of secondary alkyl halides. We still don't see tertiary alkyl halides here, right? SN2 reactions are quite challenging with those. All right, so let's go ahead and do our chime-in question. Let's see if we can, kind of connect some of these concepts. All right, so lecture 14 today. And let's go ahead and see what we think about this and sort of get some instant feedback for ourselves about whether we're understanding this or not. All right, so which starting materials can be used to make the product? There can be more than one answer. There isn't necessarily, but there certainly can be. So you're always welcome to check with somebody near you and see what they think. People are thinking at the moment. All right, so we kind of have a mixed bag here, and that's all right. I do agree that answers A and B look pretty good to me. They haven't broken any rules. We have a primary alkyl halide for both of them, and that was our big rule that we needed for our Williamson ether synthesis to work, right? Number C doesn't have the right number of carbons, right? We're starting from a phenol as opposed to a benzyl alcohol or alkoxide. And then D, we don't have something that's quite nucleophilic enough. And so remember, we're thinking about unsymmetrical ethers here. And so if we have these acid conditions, we're going to get a mixture of different ethers that form. It's not going to be a really nice uniform reaction. So that's why we don't like the option D, but I see why people were thinking that. All right, so Looks like everyone's responded. If you didn't, then let me know after class. Okay, so let's go ahead and, just write that down for our time in. All right, so the question was really asking, what is the retrosynthesis, essentially, of this particular ether? And so we could have cut it in two ways. We could have cut it here. That means if we cut it there, then our alcohol, which we use to form the alkoxide, is going to have the oxygen on it. And then we know, because it's unsymmetrical, that we need an alkyl halide. And so we can use an alkyl iodide, chloride, bromide. If we cut it on this other side, though, what does that look like? That would look like we have our alkoxide that is now on the side with the phenyl group. And then we need to have our alkyl halide on the side of the ethyl group. All right. So we'll go ahead and get on to the next learning objective, but it seems like people are sort of understanding unsymmetrical part from that chime in. All right, so we have learning objective 17F. This is another 4 Ps. All right, so this is the 4 Ps of formation of alkyl halides, as well as alcohols. And we'll see these will all funnel towards the alkyl halide at the end, but we go through an alcohol intermediate. So I'm going to add that word to this learning objective, an alcohol intermediate. And this is from the reaction of ethers and mineral acids. So mineral acids are your run-of-the-mill HCl, HBr, HI, etc. So we just learned how to make ethers, and now we're going to learn how to use ethers. All right. So as I said before, we're going to have an alcohol as an intermediate, but our final products are going to be these alkyl halides. All right, so let's see what that looks like. We're going to have a tertiary, how do I want to write this? Okay, we're going to have a tertiary alkyl halide. All right. Or sorry, not a tertiary alkyl halide, a tertiary ether. And the 2 Ps of this are adding excess of mineral acids. So say, for example, HBr, could be HCl, could be HI, those are all fine. And we're going to heat this. At the end of the day, the product that we're going to get out is going to be an alkyl halide with the halide that came from our mineral acid. All right, so if I use HCl, that would end up as an alkyl chloride. And then our byproduct, our other product in this reaction is going to be bromomethane. All right, so this is primary. This is tertiary. These are going to be important. And then the byproduct of our reaction is also, we're going to form water. All right. And so those H's are going to come from our acid. The oxygen is, of course, going to come from our ether. All right. So this is a 2-step mechanism. All right. So the first step is going to be making our primary alkyl halide. The primary one, so I put that in, differentiate the color. So the primary alkyl halide. And this mechanism with a primary alkyl halide, as you might imagine, is just your run-of-the-mill SN2 reaction. The second part of our mechanism, now we're going to generate an alcohol from this first step. And when we're making our tertiary alkyl halide, we're going to use an SN1 mechanism. All right, ready for those two steps? Let everyone finish catching up, right? All right, so let's start out with our alkyl or our ether. All right, so we have mineral acid. Mineral acid is, of course, you could write H3O+, I don't care. You could write H+, I don't care. This would probably be dissociated, so I'm actually going to write it as H+ and bromide minus. All right, so we're going to protonate our oxygen in our ether, starting the electron density from the lone pair on the oxygen and protonating that hydrogen. If you had those bound to each other, HBr, you could draw another arrow to break that bond. Doesn't really matter to me. Okay, so now what we have is a primary primary and tertiary site. All right, our oxygen is now positively charged because we protonated it. All right. So what we have here is the opportunity to have a very good leaving group. What is our very good leaving group? Our very good leaving group is a tertiary alcohol. All right. So in this mechanism, we have our protonated ether here. What I didn't draw yet is our bromide. All right, we have a bromide as our counterion that's negatively charged. All right, now let's think about, we said this first mechanism is just an SN2 mechanism. So we have the opportunity to attack our methyl group. And then we break that O-methyl bond and give that lone pair of, those electrons from our methyl oxygen bond back to oxygen to give it a neutral charge. And we've now made our first product in this reaction, right, that we're looking for, our methyl bromide. And now let's take a look what our other product is. So we have protonated it, so it has a OH bond, and now we've just made our alcohol. All right, our learning objective said that an alcohol was going to be an intermediate in this reaction. So as much of chemistry goes, we can't sometimes stop things from happening, even if we wanted them to. That's just how the world works. So let's go ahead and think about what actually happens in this reaction. So we couldn't stop it here, even if we wanted that tertiary alcohol. Instead, the second step kicks in because we have so much acid around. That's a very strong acid, all right? All right, so let's get to the second step. All right, so now we have our alcohol that we can carry down. So let's go ahead and have that carried down. All right. We also have our methyl bromide, but I'm not going to bring that along for the ride. It's already formed. Nothing else is going to happen with it. Of course, we have a lot more HBr in our reaction because we added excess. We're going to go ahead and protonate our alcohol at this point, right? We have a very strong acid. So we're going to protonate our alcohol. Remember, we said that this is going to be an SN1 reaction. Not an SN2 reaction. So above, what we had done before is we had taken this bromide, which is a pretty good nucleophile. We had used it on this primary alkyl halide to have our leaving group leave here. If we were to try to do that again, what we would have is a bromide attacking a tertiary position. And we know that that's not favorable in SN2 reactions because we know that the orbital overlap needed to make and break bonds, we're not going to be able to get favorable orbital overlap on this tertiary position. It's too sterically hindered, right? So this is where the mechanism differs from the one above. Instead of having an SN2 reaction, instead we have an SN1 reaction, which means that water, which is our good leaving group, I'll highlight that this water would be a good leaving group. All right, that leaving group's going to leave. We're going to break that oxygen-carbon bond by giving those electrons back to our oxygen. All right, so what does that mean? That means we've made water. And now we have a tertiary carbocation. That's another reason why we can do this reaction, right? Because this is tertiary. It's not going to rearrange. It's quite stabilized by being tertiary. Now we can carry over our bromide, that was our counterion before, and now this can act in its capacity as a nucleophile to make the product we're interested in, right? We don't have to worry about steric hindrance of an SN2 reaction. Instead, we just are able to get to our product, which is our alkyl bromide. All right, so this is why, you had SN1 and SN2 reactions on your 2301 review topics of the day list. As a reminder, those are on the Google Drive. You can look them up before. We need to understand some basics of those, right? So you could memorize, oh, it's SN2 then SN1, or you could just take a look at this and say, okay, I understand the steric requirements of an SN2 reaction versus an SN1 reaction, and that would help you get through this mechanism if you get stuck, all right? So there's two steps. We go through this alcohol intermediate to finally get to our two alkyl halides as our products. And if we take a look up here, that's exactly what our products are in this reaction, right? An alkyl halide that's primary, an alkyl halide that's tertiary, as well as water. All right. So what happens if we have a secondary? So here we pointed out that this is a primary and a tertiary. Now we do need to address the elephant in the room. So what about a secondary ether? All right, so without even worrying about what this other R group is, let's take a look at what that would look like here. So no matter what, we would go ahead and we would always, the first step is going to be that protonation step, right? So we would go ahead and we would protonate our ether. positively charged, one lone pair of electrons left. So are we going to go an SN1 path, or are we going to go an SN2 path? So let's take a look at what those would look like. So if we had an an SN2 path, that would mean that this bromide here that we've carried through in the SN2 path would attack here and have this as our leaving group. And then we would get to that alkyl bromide as well as our alcohol. Alternatively, we could also think of an SN1 path here. All right, so if we had SN1, what we would instead see is that our arrow would be breaking without any nucleophile attacking. So let's break that oxygen carbon bond. All right, we would end up in this case with our carbocation, and our bromide counterion would still be there. It hasn't done anything, and we would still end up with the same alcohol. Then in the same SN1 path, that's when we would form our product. So what happens in reality? In reality, it's a mixture of both. Right, and we know this from our rules regarding SN1 and SN2. Secondary carbocations are not as stable as tertiary carbocations, so that slows it down a little bit. But secondary electrophiles are not as good as primary in terms of the steric hindrance. Question? Oh, I did. Thank you. Right. All right, let's just do a couple of practice problems, all right? So let's have practice with writing the products, right? So what is going to be the product of this reaction? All right, I'm going to give you a couple of seconds to think about it. We're looking for the final products, right? So even though we might go through an alcohol here, that's not what we end up with in the products, right? So go ahead and write out what you think that's going to be. All right, so what we can think about here is we lose that oxygen on both sides, right? So we know that water is one of our byproducts. So the products that we're most interested in are going to be isopropyl chloride and then propyl chloride, right? That's the products that come from if we were to break those bonds as you have them, as they're drawn in pink. All right, so let's think about if we had a symmetrical ether. Right, what are going to be our products with HI? Let's try a different mineral acid. All right, you can always check with your neighbor and see what they have to say. Where are we going to break these bonds? We're going to break them around the oxygen, right? Meaning we're always going to have water as our byproduct, and it turns out that we're going to have two equivalents of the alkyl iodide. That's the same, right? Those are same on either side. We never draw the alcohol product. as the final product, right? Even though that's an intermediate in our mechanism, for our P4, we never draw it as our final product. All right. All right, that is all that I have for today. So thanks, everyone.